Let's take a battery, and we're showing the battery 3 times. We're going to send different currents through the battery. The battery has an EMF of 10 volts. That means if you take just 1 coulomb and you move it across the battery, then the charge should gain 10 joules of energy. But wait, it only got 9. So the total energy that the battery can give is 10. So only 9 is being given to the charge? Where'd the other joule of energy go for this 1 coulomb? It was wasted inside the battery and became heat. Batteries do this. They waste some energy. The reason is because they have their own internal resistance. So if we take 2 coulombs, or maybe a current of 2 amps, and we send it across, you don't get all 10 joules per coulomb. Each coulomb only gets 8. And if you take even more charges and you flow them through the battery, then each charge per coulomb, you do not get all 10 joules. Instead, each is getting only 7. Now, you might have thought that if this is 9 joules, if you lose 1 joule, then when this charge goes, it should lose 1. And when this charge goes, it should lose just 1. And all of these should only be losing 1. Why do we lose more joules when we send more charges through? Before we answer that question, let's make a plot. The y-axis will tell us how much energy do you have left per coulomb, and the x-axis is the current. This y-axis quantity is called the terminal potential difference, and it's this number. It's how much energy you have left for the external circuit after the battery uses some up. Okay, so let's make a plot. We need our tick marks. We started out with 1 current flowing through, and the potential difference that the external circuit got was just 9 joules for the 1 coulomb. Okay, so look over at the graph. We trace. Here's 1 amp. Right here we have the 9 volts, and we make a data point. And then we come to the second scenario. We had more current, more charges. That was 2 amps. And, oh, look at that. Each coulomb only got 8 joules. So the terminal potential difference was 8 joules per coulomb. So we come and we say, okay, 2 and 8, make a data point. And then finally we had 3 amps going through, and each coulomb only got 7 joules, so 7 joules per coulomb, 7 volts. Look at the graph, 3 and 7, make a data point. The trend you can see on the graph is a straight line with negative slope. Where is this coming from? Start with the definition of resistance. Multiply both sides by I, and what do you get? This. We're going to talk about the totals. So this total encompasses the battery plus the external circuit, and it's likewise with this total. Well, the total resistance is just the resistance of the circuit plus the resistance of the battery. And if we distribute I into everything in parentheses, we get this. Now we can start plugging things into this equation. The total potential difference is the 10 volts. Some of that is used inside the battery, and the rest is used by the circuit. So what's that? That's just the EMF. Okay, that EMF, you can see, it's divided between the external circuit, that's this, and the internal resistance of the battery. So I times R. Well, wait, R is V over I. So if we plug in V over I, the I's cancel, and you have V. And because that was referring to the external circuit, this V is the terminal potential difference. It's how much the external circuit got, which was 9 volts in this first case, and then 8 volts, and then 7 volts. Well, wait a second. If we subtract IR from both sides, you get V terminal equals epsilon, the EMF, minus IR. And you can rewrite this as V terminal equals epsilon plus negative R times I. Why have I done that? Well, look back at the graph. V terminal is on the y-axis. I is on the x-axis. So this equation has the form y equals mx plus b. When we compare these two equations, we see slope m is negative the internal resistance of the battery, and the y-intercept is the EMF. So look at that, the y-intercept, 10. That was the EMF. Let's talk more about terminal potential difference. We've got this graph. We know that less is available to the circuit when you increase current. But what exactly is there less of? Well, we could say there's less of the EMF going to the external circuit. But more precisely, terminal potential difference is the energy per coulomb because it's a voltage. So the energy per unit charge that's available to charges while in the external circuit. Think of it as how much energy the external circuit gets. Okay, here's a circuit. You've got a positive terminal, a negative terminal. Current flows this way. There's some resistance R to the resistor. And let's say you want to measure the potential difference across the entire external circuit. So you need a voltmeter. You connect it here. You need to go all the way around the entire circuit. So you might think, okay, I have to connect this wire all the way around the circuit and then bring it back at the end of the external circuit, right before we get to the battery. But look at this. You could just take this wire and move it up, and it's the exact same scenario. So when you connect your voltmeter this way, that's how you measure the terminal potential difference. It's how you measure the y-axis value. So we know what the graph looks like for a battery, but what about something like a light bulb? Let's take a circuit. You've got your EMF, positive and negative terminal. Current flows this way. Notice that this is an ideal battery. There is no internal resistance. We connect a lamp or a light bulb. First, we will measure the voltage, the potential difference across the light bulb, and we'll also measure the current. And we'll put those values in a graph. So here's the difference from what we did last time. Instead of adjusting the current and keeping the EMF fixed, we're going to change the battery. We're going to start with a 1-volt battery, then we'll swap out a bigger battery and then a bigger one. And each time we start at 1 volt, we measure the current through this thing when it's connected to 1 volt. We make a data point. And then we swap out the battery and we put in a 2-volt battery. We measure how much current flows through the lamp now. And there's the current, the new current. And then you take away the 2 volts and you put in a 3-volt battery and you measure the current, plot the data point. If you actually conduct this experiment, here's what the graph looks like. It starts out looking straight and then it curves down. That's the graph for a filament or a lamp or a light bulb. It's all the same. Now let's take away the light bulb and put something different in, like a piece of metal, a metal conductor. Again, we will adjust the potential difference that this thing dissipates, and we will measure the current. And metal conductor, this is also the graph that you get when you stop pretending wires are perfect and use non-ideal wires. What's the graph look like? It becomes a straight line through the origin. We call this on top, this type of graph, those devices are non-ohmic devices. Something like a metal conductor, that is ohmic. So what's the difference between these two? Well, think back to resistance. What's the equation for resistance? It's V over I. But wait, if you invert both sides, take the inverse of both sides, this is what we have. I over V, that's Y over X. The right side is the slope of the graph. So down here, the slope was constant. Therefore, resistance was constant. A non-ohmic device is one with non-constant resistance. An ohmic device is one with constant resistance. Why is this called an ohmic device when the resistance is constant? Well, the reason is because there is something called Ohm's law, which states the resistance of some devices is constant at a wide variety of potential differences as you change the EMF of that battery when temperature is held fixed. And this Ohm's law describes devices which have this graph.